Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, maximum number of points from grid queries. The problem states that you are given a matrix of size m cross n and a array queries of size k. You need to answer something for each of the queries here. Okay. Now, let's say we are solving queries I. So for query I, the answer would be number of cells you can visit starting from top left. Now there is a condition in the visiting. The condition is you will get the point only if queries of I is strictly greater than the value of the current cell. Okay, then only you will get the point and you will start visiting the neighbors. Otherwise you will stop. Okay, now you need to return for each query what is the maximum number of points you can get. Okay, so let's take an example. Let's say this is the grid 1 2 3 2 5 7 and 3 5 1, and the queries are 5 6 2. Now for the first query 5, let's see how much cell we'll start with top left, right? So we'll start with this one. One is smaller than 5, so that's fine, we get a point. Now we will move to the neighbors. We can move to any of the four directions, right? So we'll move to 2 or this 2. So let's first visit this 2. Now this 2 is also less than 5, so we'll get another point. So number of points we have is 2. Now this 3 will visit its neighbor, this 5 or 3. Let's say we visit 3. So 3 is again less than 5, so we get another point. Now we visit the neighbors of 3, which is 7. 7 is not less than 5, so we'll stop here. Now we'll go back. For 2 we visited 3, so now we visit 5. 5 is not less than 5, so we'll again stop here, we'll not move forward. We'll go to 1. We visited 2 previously, now visit this 2. Now this 2 is less than 5, so we get another point. So number of points till now we have is 4, right? And now for with this 2 there are two neighbors 5 and 3. This we can't visit, and this we will visit because this is less than 5. Again we get another point, which is 5. So number of points now is 5. Now we visit the neighbors of this 3, which is this 5, and this we can't visit because this is not less than the query I. So number of points that we get for the first query is 5. Similarly, if you try second one, you will see you will visit all these things, and hence the number of points would be 8. And in the last case where the query I is 2, in this case you can't visit anything more than the current one. Okay, and hence the answer is 1. So that's the problem. Hope the problem statement is clear. Now how to solve this? So first, before jumping to the actual solution, right, let's try to think of intuitively what will be the, like, how to solve it in a naive manner. So in this case, like, let's say this is the grid and we have these queries 4 9 3 7. Now for 4, like for any query I, let's say we are talking about 4. So we can visit, like we can just do a BFS starting from top left, right? We can just do a BFS and we will just stop at wherever the value is not less than 4. So we for 2 we'll start with 2. We go to 3 and 4. 3, like 4 we can't visit because 4 is not less than 4, so we'll stop here, right? Now for 3 we can visit 3, so we'll visit its neighbor as well, which is 3 and 6. So 6 we can't visit because it is not less than 4, so we will visit 2. Like this is now stopped. Visit 2. 2 has neighbor 2 and 7, right? Sorry, 1 and 7. Now we can't visit 7 as well. Now for 1, neighbors is 5 and 8. We can't visit both 5 and 8, right? So basically we can do BFS for each uh, queries here, and with BFS we can get to know which all cells we can visit. So for 4 we saw that we can visit this thing, and hence the answer is 4. We can do this for every query here, and we'll get the answer for each of these queries. Now what will be the time complexity of this approach? Time complexity would be for each query you are iterating over the, or we are doing a BFS, which can in worst case take order n cross m time, right? So this is the time complexity of BFS in worst case. Now you are doing this for each of the queries that you are given, right? So the complexity would be n into m into q, where q is the number of queries and n into m is the size of the grid. So as per the problem statement, the size of the grid is 10 to the power 5, number of queries is 10 to the power 4. So this complexity would not pass. Okay. Now you need to reduce this. Now what exactly you can reduce? Think about it. Which of this factor you can remove? You can't remove q, right? Because you have to do something for each of the queries. So this q factor would be there. Can you remove n or m? The answer is again no. You can't remove like either of n or m. The reason is you have to visit the entire cell at least once. So you can try doing something such that you are not multiplying these factors, or in other words, you are not like for each query you don't need to traverse the entire matrix, right? So what exactly you can do here? So let's say you are solving for 9, right? Now if you are solving for 9, the answer for 9 would include everything that we have included for 4, right? So 9 is greater than 4 and we are stopping where we are receiving 4. So whatever we have included in 4 will be there in 9, right? So based on this, what we can do, we can just optimize. We will not start the BFS from top left again for 9. Instead, we will start the BFS from the cells which we left over from 4. So for, if you remember, for 4 we have visited this thing, right? Now for 9 we will start the BFS from the neighbors of these nodes which we have left over. So this 4, 6, 5, 8, 7. These are the neighbors of the visited nodes, and we have left over them because they are not greater than 4. They are not less than 4. So for 9 we can keep this part as it is, and we can start visiting these neighbors first. So for 4 is good, like for 4, 4 is less than 9 now, so this can be visited, so we will visit this. Similarly, we will visit its neighbor as well. So that's the idea. Basically, we will try to build upon whatever we have already visited or whatever we have already done for the previous queries, right? So that's the basic idea. Now remember, you can do this only because all the queries that are given to you, like all the queries are given to you beforehand. So this entire query array is given to you beforehand, and that's why you are able to, like what we can do is we can just sort these queries. Let's say this 3, 4, 7, 9, right? Now we can just sort this query and then we'll start the BFS and first find the answer for 3, right? Now whatever nodes we have been visited, we will keep it as it is, and then we will start the BFS starting from building upon whatever we have visited for 3 and go up to 4. Whatever we'll visit for 4, we will keep as it is, and then we will start it and visit 7. And finally, we will build upon that particular nodes or set of nodes that we have visited and query for 9. So basically, what we are doing, we are visiting, we are not doing the entire BFS always. We are stopping at the given query position. But for the next one, we are not starting over. Instead, we are building upon whatever we have visited before. So in total, like this entire thing is BFS, one BFS, right? One single BFS. So total time that could take for this entire thing is n cross m, right? Over all the queries. Like over all the queries, if we can do this BFS, our complexity would be n cross m plus q. Why plus q? Because we are iterating over the entire array as well. But we are not doing entire BFS for each of these queries. Instead, we are doing BFS only once across all the queries, right? So that's what the time complexity would be if we are able to do this efficiently, right? Now, that's the basic idea. Hope this idea is clear. Now, if this idea is clear, let's just try to think how we can do this actually. Okay, so we have sorted the queries. Let's say this 3, 4, 7, and 9, right? Now let's start with 3. Okay, let's start with 3. Now if we start with 3, this 2 will be there, right? That's okay. Now can we move forward? Answer is no. This is the neighbor which is smaller than 3, which is not smaller than 3, and this neighbor is also not smaller than 3, so we can't move forward. So the number of points for this 3 would be 1, right? Now if we move forward with 4, okay, let's take a step back. Let's make the queue as well. That will make things more clear. Okay, so initially q has this 2, right? This 2 at 0 comma 0. This is 0 comma, sorry, let's put 0 comma 0. Okay, so initially you have 0 comma 0. Now once you visit this, like we visit this, right? And now we will put the neighbors, which is 0 comma 1 and 1 comma 0, right? Now okay, we can visit the neighbors in any order, right? So for now, let's assume that if we put 1 comma 0 and 0 comma 1, right? Let's say we put this neighbors in this fashion. Now what will happen? Think about it. You know that you can't move forward with 1 comma 0, right? And similarly you can't move forward with 0 comma 1, so you keep them as it is. Now you get 4. Now for 4 you will see, okay, if 1 comma 0, is 1 comma 0 greater than 4? The answer is no, so you will keep it as it is, right? Now for 0 comma 1 you will see, okay, 0 comma 1 is smaller than 4. Answer is yes, 3 is smaller than 4. So we will start visiting its neighbor. So you will remove this one and then visit its neighbor, right? So is this optimal? Like, is this it? Will it lead to our target, that we will be doing the BFS, or we will be visiting every node exactly once? That's where the complexity would be order n, right? But will it help in this case? The answer is no, because if you think, for 3 you have visited these two nodes already, right? And now for 4 again you are visiting this node, and then like saying that, okay, I can't visit it, and then you start visit this node. So, or you already visited some nodes twice. Now for next query 7, again you will again visit this node, right, to check whether this node can be taken now as well, and then you will visit the next nodes, right? So basically what I'm trying to point here is, we are not actually visiting every node exactly once. So this complexity is still not order nm, it is still order nmq if we just do it in this fashion. So we need to, like, how can we make it order nm? We can make it order nm by ensuring that we are visiting every node exactly once, right? Like, we are not traversing the entire queue to figure out that I need to stop. That's the basic point. Currently we are traversing the entire queue, and then we are saying that, okay, I can't move forward anymore, right? But if we are able to tell this by looking at the first element in the queue itself, then it can be like, we can decide this much earlier, right? The problem we are facing previously was, we are iterating over the entire queue and then figuring out, okay, I can't move forward. Like, I have visited all the neighbors. Now there is no neighbors which I can further explore. But now what we are saying, if we can somehow say that, okay, looking at the first element of the queue itself, if I can say, okay, I can't, if I can't visit this, I can't visit this as well. So if you think about it, this statement leads to some kind of ordering. If you have some kind of ordering in your queue as well, then you will be able to say, okay, by looking at the first element, I can say whether I need to move forward or not. Okay, so what, instead of this kind of queue, you will maintain a priority queue, right? And what will be the sorting order of that priority queue? It will be the value of the nodes. So let's again take the same case, and let's start from the beginning. So let's say 2 and 3 are not visited. Okay, now we'll start from the 3. Now we are at 0 comma 0, right? So what we'll put in the queue, we'll put that current value is 2, and I am at, like, this 2 is at 0 comma 0. So we'll put three things. Okay, now 3 comes, right? 3 comes, 3 say, okay, there is 2 at the beginning. Is 2 less than 3? Answer is yes, so let's pop it out. Okay, pop it out and visit its neighbor. So we popped it out, so we got 1 point, and we are visiting its neighbor, so which is 3 and 4. So what is the 3, like what exactly you will put for 3? 3 would be this 3 comma 0 comma 1, right? And similarly for 4 it would be 4 comma 1 comma 0, right? Now you will put this in sorted order, so you will put 3 here first and then this 4 here, right? Because you are maintaining the sorted order in your queue. Now again you visit, like currently you are at 3 only, right? So now you will look at, okay, what is the top element? It is 3. Is 3 smaller than 3? Answer is no. So we'll not explore 4 at all. Previously we have explored 4, right? And then we have said, okay, we are done. But now we are not exploring 4 at all. By looking at 3 itself, we are saying, okay, we are done. Because if 3 itself can't be popped out, anything else can't be popped out as well, because others are greater than 3. Okay, so that's why we will not pop out 3, and we will say the answer for 3 is 1. Okay, now we will get at 4. Now for 4 again we will do the same thing. We'll look at the top element. Can we pop this top element? Answer is yes, we can pop it. So let's pop it out, right? And let's visit its neighbor. So neighbor is 2 and 6, right? So what is the value for 2? So the value for 2 would be 2 comma 1 comma 1, right? And what is the value for 6? The value for 6 would be 6 comma 0 comma 2, right? So again you are maintaining this queue in sorted order. So this is already lost, right? Now you will put 2 here, okay? 4 will come here, and now 6 will come here, right? This is your sorted order. Now you will again, for 4 you look at the top. What is top? 2. 2 is less than 4? Yes. So we can pop it out. Let's pop it out as well. So you will pop this 2 as well, and now visit its neighbor, right? So again, when you visit this neighbor, you will get 1, like this neighbor is 1 and 7, right? 4 is all like 1, 7 and 4. So 4 was already visited, like 4 is already present in the queue, right? You can't push this 4 again, because if you push this 4 again, you will be getting more points. So that's you don't want, right? So basically you also need to maintain a visited array, where you will say, okay, these all are something which I already visited. So this 4, 2, 3, 2, 6, and 1 are something which I already visited. So not one. These are something which I already visited. Now we'll not visit this again. So for neighbor of 2 is 3, 4, 1, and 7. So we'll not visit 3 and 4, because 3 and 4 are already visited. We'll visit just 1 and 7, and we will push it in the queue in the same fashion. Okay. So hope the entire solution is clear. So what we are doing is, we started with a very brute force approach, which is n cross m cross q. Now we figured out why it is slow. It is slow because we are doing the exact same thing multiple times in the row. And we saw that we can avoid this entire thing by just sorting the queries and then doing it incrementally. But by sorting the queries and doing it incrementally also doesn't help much, because we are actually iterating over the entire queue to figure out we are done. So to avoid that, we just sorted the queue as well, so that by looking at the first index itself, I can say whether I need to move forward or not, right? So finally, after doing that, we are seeing that we are visiting, or we are popping every node exactly once. And because we are popping every node exactly once, we we are saying that, okay, either, like if we, let's say, query this node, so either we'll pop it or we'll move to the next node, right? So either this is less than 4. Let's say, let's talk about 2. Either 2 is less than 4, and in this case 2 will be popped out, or 2 would be greater than 4, and we will just move forward with 4. We will not do anything with this 2, but we'll move forward with 4. So basically one query is now answered. So in with everything, like with every node, we are doing one of two things. Either we are popping it out, or we are moving forward with the query. So the time complexity would be q log n. Like for each of these queries, we will be encountering one value. Like we will be basically querying one value to figure out whether I need to move forward or not, whether I'm done or not, right? Or you will be popping out one element exactly once. So basically n cross m into log of n. What is capital N? Capital N is equals to n cross m, basically number of nodes. Okay. So this is the final time complexity, and this will pass as well, right? So hope the entire problem is now clear. Let's quickly look at the pseudocode, and then we'll look at the code as well. So the pseudocode is very similar to what we discussed. We sorted the queries, right? And we are maintaining the query index as well, because finally we need to return the result, and result should be returned in the order of the queries. So that's why we are maintaining the return indexes as well. Now this is the nodes. Now again, I use set, you can use priority queue here as well, that's completely fine. And this priority queue should be sorted in decreasing order, right? And the set is by default sorted in decreasing order, that's why I use set. Doesn't matter much, right? So you are seeing, okay, what is the max value. Like for each query you are doing the same thing, you are finding out what is the max value. And then what we are doing is we are figuring out, like we are just popping the nodes from the top until we can pop it, or basically until the value is less than the maximum value. Okay, or what is the maximum value? Maximum value is the current query value. Okay, now once we pop it, we increment the points as well, because points is now incremented. We get 1 point by popping a node, and then we will visit the every neighbors of this node dot row and node dot column, right? And if this neighbor is already visited, we will continue. Otherwise, we will mark this as visited and push it in the node, right? Now notice that this push is actually in the set, so this will go in its correct place. Okay, now finally we'll keep on doing this until we are saying that we are done with this, we can't pop for much further. Okay, and finally we will just populate the result of this particular query index as points. Okay, so hope this solution is clear. Let's look at the code is again exactly similar. What we are doing, we are maintaining this queries and index, so we are pushing queries at j and index j, right? And we are sorting these queries. Now after that, with we have this result, right? And we have this visited array and total visited, this is nothing but points, right? Now we have this set of nodes. Initially this contain 0 0 and grid 0. So nodes have three things: row, column and value. Okay, so this is the row, this is the column, and this is the value, and it is sorted by value always. So this visitor of 0 0 is true, we marked because we already push it in the set already, so we just mark it as true. And then we visit every, like we visit every queries one by one, and that will be our max value. Now finally we like go through the entire, like we just check what is the value of the first node, or what is the smallest value in the set. If it is less than max value, we will pop it and visit all its neighbor. And we'll keep on repeating this until we have no more nodes, or the top of the node has greater value or equal value as maximum value. And we will just assign result index as total visited. Now we are incrementing total visited inside this node, entire this uh, while loop, whenever we are popping something, because when we are popping something, that's the time we will get that point, right? So we are incrementing it here, and now after that we are visiting all its neighbor, that's it. So neighbor visited is very standard code. Like we just have these four neighbors, and we'll visit this. We'll check whether it is valid cell or not. If it is valid cell, whether it is visited or not. If it is not visited and it is a valid cell, we'll mark it as visited and push it in the node, right? So that's pretty much it. If you have any doubts in this problem, please post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe to the channel if you haven't already. And I will see you in the next one. Thank you.